We find out by studying the Lake Missoula flood just how devastating the Genesis flood was, but we have to extrapolate out. And the Lake Missoula flood was a strong assault on uniformitarianism. The evidence for the Lake Missoula flood is obvious all over, and yet they rejected it for 40 years because it's too biblical. Even now, we don't expect them to find evidence for the Genesis flood because of that strong bias that just clouds their mind.
Welcome to the Flood Geology series, the programs where leading scientists take you exploring around the world to view the geologic evidence for the biblical flood and how its effects shaped the earth during and after this worldwide cataclysmic event only 4,300 years ago.
Here we are in northwest Montana, about 6 miles northwest of the town of St. Ignatius, about 30 miles south of Flathead Lake. And we're in the area where glacial Lake Missoula ponded at the peak of the Ice Age. Now, glacial Lake Missoula probably was the second largest flood on Earth. The Genesis flood was number one. But the Genesis flood was about 10,000 times the size of Lake Missoula flood, which was monstrous, as you will see. Well, we learned several things by studying the Lake Missoula flood. First of all, we find out by studying the Lake Missoula flood just how devastating the Genesis flood was. But we have to extrapolate out maybe 10,000 times. Secondly, we can study what this flood did. Since it's the second largest, we can look and see some of the landforms or features it formed, and we can relate these to some features on the surface of the earth formed during the Genesis flood so that we can understand that floods formed these features. Another aspect of learning about the Lake Missoula flood is that we find out why mainstream scientists will never accept the Genesis flood, because the evidence for the Lake Missoula flood is obvious all over, and yet they rejected it for 40 years. There are especially two aspects of the Lake Missoula flood that impinge upon biblical Earth history. First of all, how many floods were there? The secular scientists, first of all, said there was one. J. Harlan Bretz, when he first studied this area starting in 1923, believed in one flood. But then, because of a peculiar ash layer in some rhythmites in eastern Washington, they decided that, well, there was probably 40 floods. Then in northern Washington, in the Sandpoil Valley, they saw what they say almost 100 of these rhythmites. And therefore they said there was about 100 Lake Missoula floods. So that means Lake Missoula has to fill up about 100 times and then break. If it takes 50 years to fill up on the average glacial Lake Missoula, which is an underestimate, that's about 5,000 years of time at just the peak of the Ice Age. And yet they say there's 50 ice ages in regular succession now based on deep sea cores. So that's a lot of Lake Missoula floods and lots of time. So this is a challenge to biblical Earth history, which teaches a young Earth. So we will be examining how many floods there were. A second aspect is that if there was a glacial Lake Missoula, that means there was an ice age, because a lobe of the Cordilleran ice sheet from British Columbia came down through northern Idaho and blocked the Clark Fork River and created an ice dam and backed up the lake here. So that means there was an ice age after the flood. Well, here we see in the background horizontal lines that are very even. These are shorelines from glacial Lake Missoula on the northern slopes of the National Bison Range. These shorelines are all over where glacial Lake Missoula was. They are down the Bitterroot Valley, and they're up in this area just southwest of Flathead Lake. The most famous ones are around the city of Missoula. They're very even, and they're approximately 35 feet on the average. Well, if there's any icon that represents the glacial Lake Missoula flood, it is these shorelines. Because they're all over, you have to have a lake for a flood, and so it gives you the dimensions of the lake. Also, in some aspects where the lake occurred, there's raised deltas where a stream came into the lake and it formed a delta. And then when Glacial Lake Missoula broke, that delta is left hanging. So these are evidence that the lake existed at one time. Well, we're about 2,500 feet above sea level here, and based on the highest shorelines, the lake was about 4,000, 4,200 feet. So that means that the lake was about 1,500 to 1,700 feet above me here. From the highest shorelines, we can determine the volume of the lake. The volume of the lake turns out to be 540 cubic miles, twice the volume of Lake Erie. It was 1,000 feet deep over the city of Missoula and 2,000 feet deep where the ice dam was in northern Idaho to the west. Glacial Lake Missoula was blocked by a finger of the Cordilleran ice sheet that covered British Columbia, and 4 lobes came down into the northern United States: the Puget Sound lobe, the Okanagan lobe, and the Purcell Trench lobe in northern Idaho, and the Flathead lobe, which ended just north of us. The lobe in northern Idaho was the one that blocked the Clark Fork River, and so as ice was melting at the peak of the ice age, it was filling up. And we can estimate how deep the ice was that blocked it. It was approximately 2,500 feet thick. The lake was 2,000 feet deep along the Montana-Idaho border. We can tell by the surrounding north-south mountains that were not glaciated about how deep it was, so it was about 2,500 feet. Ice isn't going to hold a lake that's increasing in volume year by year for very long. So one day, it just probably lifted the ice or tunneled through the ice, and within a matter of hours it just broke through and emptied out in 2 days. On this field trip, I'm going to show evidence that there was only one large Lake Missoula flood. Now, there might have been a few smaller ones afterwards that were insignificant. So the question is, what's the explanation of those shorelines up there? Well, because I actually walked up them and gave an estimate of the vertical distance about 35 feet, that they're very regular. I believe that each shoreline is probably 1 year of filling of the lake. In 1 year, it raises 35 feet on the average and protects the shorelines below it, and it continues to do that, and that's why it was protected. Otherwise, if each shoreline represents one flood, like the secular scientists believe, you'd have a chaos of shorelines where each lake would come up and it would destroy parts of the other shorelines that were made from previous lakes. It would just be a mess. But these are so even over this area that I believe it was just one filling in approximately 80 years at the peak of the ice age. Now, these shorelines are just as distinctive on hard rocks as they are on soft rocks. They haven't been eroded. This tells me that Glacial Lake Missoula and the Glacial Lake Missoula flood was recent. Here we are about 5 miles north of St. Ignatius in northwest Montana, in a valley that was covered with about 1,500 feet of the waters of Glacial Lake Missoula. Behind me, you see a gentle rise. It's an east-west rise, about 100 feet. This was considered the Mission Moraine and was believed to be the furthest south extent of the Flathead lobe of the Cordilleran ice sheet that covered British Columbia. And this was believed for 100 years until a man decided to examine the sediments in that rise and other places and found out that it wasn't moraine material. In fact, he found out it was lake bottom sediments of Glacial Lake Missoula. Furthermore, he examined these bottom sediments and found no channels. It was all just evenly bedded all the way down to bedrock. Well, there's channels on top of it. So, to him, this was evidence of one large filling of Glacial Lake Missoula, because if Glacial Lake Missoula filled and emptied, these lake bottom sediments would be filled with channels and other evidence of erosion in the time it takes to fill the lake. And because there aren't any, this is pretty powerful evidence that it was only one Glacial Lake Missoula flood. Well, it's interesting that there's lots of lake bottom sediments in this northern part of where Glacial Lake Missoula used to be. Even though the ice dam broke, The water was rushing out at 80 miles an hour through Eddy's Narrows. Then the question is, why do we have this ridge back there? Well, here's what I think happened. To the south of us is the National Bison Range and a bunch of hills, and to the east of us is the high Mission Mountains. So as Glacial Lake Missoula was draining out that way, it was kind of converging in here and going around the northern Bison Range out through the valley to the south and into the Flathead River. So I think this was a faster currents in here and eroded the lake bottom sediments in here, and that's why this ridge here is east-west, is because it just was going out mainly to the west, and it just scoured near the mountains here. We're on the Polson Moraine, just south of the city of Polson, overlooking Flathead Lake in the background. Now this is a real moraine. It's a ridge of gravel and sand where the glacier pushed it out and deposited along the edge. It's a terminal moraine of the Flathead lobe of the Cordilleran ice sheet. The Cordilleran ice sheet covered practically all British Columbia. East of the Rocky Mountains, we had the Laurentide ice sheet that covered central and eastern Canada and was also in the northern United States. This is the furthest extent of the ice sheet. So Glacial Lake Missoula was ponded right against this ice sheet and was approximately 1,200 feet deep right here. And of course the melting of the Flathead lobe added to the water. As the glacier moved south, because of its surface slope towards the south, it probably scooped up a lot of debris from Flathead Lake and over-deepened it. That's probably one reason why we have this moraine right here and Flathead Lake behind us. We are at Camas Prairie in northwest Montana, one of the most famous localities associated with the Lake Missoula flood. As you see in the background here, you see some long rolling hills. Well, those are ripple marks caused by when the Lake Missoula flood was moving south out of the Little Bitterroot Valley that way, and it was moving over these ridges, and it formed these ripple marks about 2 miles wide, up to 30 feet high, going way down in this valley. They're gravel ripple marks. Now the water was coming out of the Little Bitterroot Valley, which was banked against the Flathead lobe of the Cordilleran ice sheet. And the Little Bitterroot Valley is loaded with lake bottom sediments, which have been partly eroded, especially in the north, but they're very flat on the top. And along the edges, there's shorelines from the lake all over the place. When the lake broke in northern Idaho, the water started rushing across this area because it was 1,000 feet deep at this point. So as it's rushing out, it formed these ripple marks. It is interesting that J. Harlan Bretz, who was the original discoverer of the Lake Missoula flood, he started publishing papers in the journal Geology, the Geological Society of America Bulletin, starting in 1923. Bretz's work in eastern Washington was really a great piece of geological detective work. He started this by looking at geological maps just published for eastern Washington. He didn't know where the water came from, yet he was able to deduce from the geology and the geomorphology, the shape of the surface there, that there was a massive flood. It was obvious. He was able to put this all together to come up with a monstrous flood, even though he never knew the sources. The data spoke for itself. And he ended about 1932 with a long monograph on Grand Coulee. And it's interesting, in that time, in 10 years, he never knew the source of the water. He kind of considered it came from the north, from the Okanagan lobe of the Cordilleran ice sheet, ponded in there under the ice or something like that, or a lake banked up against the ice and then it broke. That was his original thought. So he really never knew the source of the water. He didn't know about Glacial Lake Missoula. But it's interesting, a man named Pardee, a geologist named Pardee, knew about it. And when Bretz was describing all the many hundreds of features as evidence of the Lake Missoula flood back at a meeting of the Geological Society of America, Pardee was there, and he knew about Glacial Lake Missoula because he was the one who did the research in this area. He knew about the Camas Prairie. And the evidence of it is for catastrophic flow of water coming over this ridge and out this valley. He knew this, but he kept quiet about it because his supervisor, Richard Foster Flint, which was one of the most well-known quaternary geologists, or ice age geologists in the world, was strongly against the Lake Missoula flood. Pardee kept quiet because the world view of geologists was not only naturalism, that nature is all there is, but a part of naturalism is that you only use present processes to explain all the past rocks. And that's called uniformitarianism. And that was the world view that was predominant at that time and still is at this time. This worldview started during the Enlightenment, called the Age of the Enlightenment, starting in the 1700s, when scholarly people rebelled against the Bible and decided they were going to figure out everything by pure reason. So they reasoned that, well, we have all these rocks to explain and fossils to explain, so what principles do we have? Well, we can only use what we see going on today to explain all the past. So that assumption became dogma starting in the 1700s, even before the principle of uniformitarianism became formulated by Hutton in 1795 and Lyell between 1830 and 1833 when he published his Principles of Geology. It was used 50 to 80 years before that. So at the time of the Lake Missoula flood controversy, but in the late and mid 20s to the early 1930s, that was the principle they were looking at. And because of that principle, they said they don't believe in big floods. They don't even believe in too many small floods, because you have to only use present processes, which are small little floods on rivers or flash floods to explain things, or a river delta, to explain all these vast array of sedimentary rocks that sometimes go for hundreds, even thousands of miles. So they were stuck with that. And one geologist said that we can't accept the Lake Missoula flood because it's too biblical. This worldview retarded the science of geology with the Lake Missoula flood, and I believe with other issues in geology. And the way it did this is that if they stuck with just the empirical observations, they would have concluded there was a massive flood. Then they would have said, well, how did it form, and so go on from there. But no, they had to reject it because it was against their worldview. And it's really interesting in showing the action of this worldview with some of the other geologists is that other geologists tried to explain the features Bretz was describing in the geological literature, and they would dream up these strange, weird ideas. Like one guy named Allison dreamed up an ice dam, where icebergs were floating down the Columbia River, and they came together in a narrow area of the Columbia Gorge, and they backed up water 1,000 feet up in eastern Washington, causing the scabland features. That was one idea. Then another guy named Hobbs, had the ice going way down to near Walla Walla, and due to melting and all this, it formed the scabland features. Many guys who rejected it, I'd say probably 90-some% of it never even came out here to look at it. It was just rejected out of hand because of their biases. But Richard Foster Flint, one of the most famous quaternary geologists, came out here to do research. And even seeing all these things, monstrous bars and rhythmites and other evidence of a catastrophe, he still interpreted a slow, gradual melting of the ice sheet to the north, forming these features slowly over thousands of years. So his uniformitarian bias, he was totally blinded to the catastrophe of the Lake Missoula flood because of this. He was operating out of his bias. He was using an interpretation already made. It's all slow processes over millions of years, and went out and interpreted catastrophic features in terms of slow processes over millions of years. It's quite a history showing why they will never see evidence of the Genesis flood. They can see the huge catastrophe, like I see it all over the place, and yet they don't see the same things, and they never will, or very few will, I should say, because of that strong bias that just clouds their mind. And so that's the way it is in geology during the time of Bretz, and the way it is now. But they don't realize that it's a worldview that they're expounding, and it's based on assumptions that are unprovable. And the Lake Missoula flood was a strong assault on uniformitarianism. Well, here we are at Rainbow Lake. about 8 miles northeast of Perma in northwest Montana. And we're about 3,500 feet above sea level. And this lake was gouged out as glacial Lake Missoula broke. And the water was coming at us from the east, one from the south, converging in here. And when you have converging water, it accelerates the water. So it accelerated and dug out this trench, making this long east-west lake. And the material it dug out formed a gravel bar a couple miles long at the other end and a couple 100 feet high, which has huge boulders in it. It's typical that in the Lake Missoula flood, when the floodwaters accelerated, it dug over deepened trenches that are long and skinny in the direction of the flow. There's a number of them in the path of the flood. Also, this rock that we're on right here, it's layered, tilting to the west about 15 degrees. This is all argillite, which is a metamorphic shale. This is part of the belt supergroup rock that goes from Helena to Spokane. It's about 400, 500 miles in diameter, and it's over 20 kilometers thick. We know that because it's uplifted and folded. The top couple of kilometers got eroded off, and we can't find the bottom, so it's probably 25 kilometers thick at one time or more. This argillite is the same type of rock that is pretty unique to this area, that is found as a large boulder from the Lake Missoula flood near McMinnville, Oregon. We are along the Flathead River between Perma and Paradise, Montana. Glacial Lake Missoula was about 2,000 feet above us. And when the dam broke, the water was rushing through here pretty fast as it's moving and carrying all kinds of debris. And it formed a gravel bar in a valley in the background there on the other side of the Flathead River. It's called an eddy bar. There are three types of bars: a longitudinal bar that goes along a drainage. There are eddy bars that you get sharp changes in the channel and cause flow like this, an eddy. And you get eddies in valleys where the flow is going over the valley and kind of eddying back, forming a bar. Those are the three types of bars associated with the Lake Missoula flood. Well, here we are just east of Paradise, Montana, and in the background is another eddy bar, a little tiny one with a house built on it. In the background is the Clark Fork River. This is the river that was dammed up to form the lake. Just up a few miles, the Flathead River comes into the Clark Fork and forms an eddy bar going around like this. Well, here we are about 15 to 20 miles west of Plains in the valley of the Clark Fork River, and we're at Eddy's Narrows, which is the most narrow spot the Lake Missoula flood was flowing through. It's about a half a mile wide. Mountains are at least 2,500 feet. The lake was 2,000 feet deep here and was rushing through here very fast towards eastern Washington. It's rather difficult to estimate the speed of the flow, but it can be done scientifically. Along the ridges where the water scoured and you take the slope, you can estimate it. One estimate is 45 miles an hour. Then for a long time it was 60 miles an hour, and the latest literature says now it was about 80 miles an hour flowing through here. Just imagine that much water moving through here 80 miles an hour. It's going to cause tremendous erosion, and that's why we sometimes have eddy bars up in the side valleys. And as it's moving through eastern Washington up to 60 miles an hour, it's a tremendous erosion. It eroded about 50 cubic miles of basalt and about 100 feet of silt on top of the Columbia River basalts that eroded. That much is unimaginable, but just think of the Genesis flood, which is probably 10,000 times the scale of the Lake Missoula flood. Just imagine the amount of erosion and transport, fast currents and deposition you get in the Genesis flood. Well, here we are at Lake Ponderay in northern Idaho. This was where the ice dam occurred. The Purcell lobe of the Cordilleran ice sheet came down this valley, north-south valley into northern Idaho and went further south here, maybe about 20 miles or 30 miles. It was about 2,500 feet deep because the mountains in the background there were unglaciated at the very top. This ice dammed up Glacial Lake Missoula just a little ways to the east. Now the Clark Fork Valley was unglaciated. So as this lobe moved south, it also moved east up the Clark Fork Valley, and as it moved east, it had rocks in it, and it produced striations along a cliff up there near the town of Clark Fork. Lake Pend Oreille is an overdeepened lake. It's a maximum of 1,150 feet. It's the 5th deepest lake in North America. And it was likely overdeepened during the Ice Age because it seems like during the Ice Age when you had a valley filled with ice, it tended to overdeepen that valley, probably due to meltwater under pressure, just eating out the bottom. This is very common in previously glaciated areas where ice filled up valleys and overdeepened the valleys. They're called fjords along the coast of British Columbia, Norway, and Scandinavia. Not far from here in Glacier National Park, which was glaciated during the Ice Age, we had Lake McDonald, which was overdeepened. It's a maximum 450 feet deep. When Glacial Lake Missoula, 2,000-foot deep lake, broke through the ice dam here, it rushed down the Rathdrum Prairie and through Spokane, spreading gravel through that whole area. That is why that area, including Spokane, is a terrific aquifer. There's lots of water down there in that gravel. I think it's something like 600 feet deep of gravel. Also, this gravel formed a dam in front of another valley to the south and formed Lake Coeur d'Alene after the flood was over with. Just imagine the ice being 2,500 feet deep here, blocking the lake in the Clark Fork Valley, 2,000 foot deep. Just almost unimaginable. Just imagine when Glacial Lake Missoula broke through the ice dam. It came rushing through northern Idaho, and then it came through eastern Washington and carved up eastern Washington. When it came out this way, it entered another glacial lake, Glacial Lake Columbia, that was dammed up by the Okanagan lobe, which is to the west of us. And it filled that lake up really quick, and that overtopped at a number of locations. One is just southwest of Spokane, where I-90 follows. Another is over near Grand Coulee. And then there's a few little channels in between and to the west of Grand Coulee called Moses Coulee. So it overtopped in all these areas, and it converged further south. Now, when it went through this area, it eroded material that was about 100 feet of silt. It came through this area called the Cheney-Palouse scablands, and it tore up the silt and eroded down to the basalt. That's typical scablands, where you have the basalt is left as mesas, and so it's very rough and it's difficult to farm, so they don't farm it. But it left silt hills in places, and that's where they farm. You can see the image from space because of the different colors of silt and basalt of the flood path. Also, as the flood moved southwest, going through here, it caused some overdeepened lakes, probably because of local accelerations in the flow. Behind me is Sprague Lake, another overdeepened lake in the flood path that's orientated southwest-northeast. And it's typical of other lakes out that way, southwest of Spokane, that are orientated in the same direction. Rock Lake being the most significant one, about 7 miles long. When it was going through eastern Washington, first of all, the flood was about 600 feet deep over Spokane, Washington. Can you imagine that, 600 feet? And it came through this area, moving up to 60 miles an hour at times. It was going through the Horse Heaven Hills to the southwest of us. It was about 1,000 feet deep through there. And then it was going through the Columbia Gorge through into the Portland, Vancouver area. And it was going 80 miles an hour through the gorge. And we know from calculations due to what's called the slope area method that it was going 60 miles an hour at times through eastern Washington. And by the time it entered Portland, it was about 400 feet deep. Well, just multiply that by 10,000 times and it gives you an idea of the power of the Genesis flood on erosion and transport and deposition. Just unimaginable forces during the Genesis flood. We're at Odessa, Washington, out in the middle of central Washington. Where we are right now is between the two main channels of the Lake Missoula flood. The flood did come through this area in narrow channels, of which this is one of them right here. It's called Crab Creek, which the town of Odessa is down there in the bottom. And this is a long east-west trough carved by the Lake Missoula flood, about maybe 400 feet deep and about 2 miles wide. This is one of the main ones through this area between the two main tracts of the Lake Missoula flood. The tract to the south of us called the Toulouse-Cheney tract, and the tract to the northwest of us through Grand Coulee. Well, here we are above Lake Roosevelt, which is dammed up by Grand Coulee Dam there, which is about 300 feet deep. And this lake goes way up into northeast Washington. This is the valley of the Columbia River. It's about 1,500 to 2,000 feet deep. And then at the end of the flood, the Ice Age developed. The Ice Age formed more or less in place. It didn't have to start in northern Canada and move down. It was almost like instant winter, caused by the volcanic ash and aerosols trapped in the stratosphere and all the warm ocean water producing abundant evaporation and moisture. It formed the whole northern United States and practically all of Canada. As it formed here, the edge formed lobes, and those lobes moved down valleys. There's a valley that goes up north into British Columbia. It's north-south. A lobe developed in that valley and descended further south. And so glaciers move by the slope of their surface. A lobe of the Cordilleran ice sheet, which covered most of British Columbia, filled up the Okanagan area. It's called the Okanagan lobe, and dammed the Columbia River, just like the Purcell lobe dammed the Clark Fork River, forming Glacial Lake Missoula. So right here we had a lake similar to Lake Roosevelt here, about 1,000 feet deeper at least. It's called Glacial Lake Columbia, and they believe it backed up clear to Spokane, Washington. At that depth, it was close to the tops of the ridges to the south. When the Lake Missoula flood broke, it filled up Glacial Lake Columbia, and it overtopped that ridge from southwest of Spokane to this area in several areas. Two main areas, just southwest of Spokane, forming one scabland tract called the Cheney-Palouse tract, and one over here, 100 to 120 miles west of Spokane, because the ice was banked up here. And Glacial Lake Columbia rose from adding all that water from Glacial Lake Missoula. It overtopped the ridge right here. The ridge is about 2,800 feet or something like that. Glacial Lake Columbia was near the top, and so it overtopped and carved Grand Coulee that way. Also, the water went a little bit further to the west and carved another valley just 10 miles west of Grand Coulee called Moses Coulee. Now, Moses Coulee is only about 400 feet deep. Now, Grand Coulee was cut 900 feet deep and 50 miles long during the Glacial Lake Missoula flood. So a lot of water came through. In fact, you added a lot of water to Glacial Lake Columbia because it just carved the ridge down to a notch, 900 feet notch. And the notch is still on a ridge, so it's sort of like a wind gap. Here we are at Banks Lake in the upper Grand Coulee. Banks Lake is an overdeepened lake caused by the Lake Missoula flood. There's a series of overdeepened lakes clear through the 50 miles of Grand Coulee, which Soap Lake is probably one of the most significant ones at the southern end, of which it was overdeepened by currents moving probably 60 miles an hour, and it threw up this huge gravel mound in front of it called the Ephrata Fan, an expansion bar. From the top of the expansion bar, probably the depth of the lake is about 300 feet. And so it overdeepened that Soap Lake, and there's several other overdeepened lakes. Now, this is a natural lake caused by the Lake Missoula flood. The government decided that for irrigation in Washington, they were going to raise it. So they put in a dam of maybe about 60, 70 feet high here. At the southern end, they put in a dam maybe about 20 feet to raise the level of Banks Lake. They get the water, this extra water up here, by pumping it uphill from Lake Roosevelt at Grand Coulee Dam, just down that way. Well, this is the area where Lake Missoula flood spilled over a basalt plateau. Before the flood, this whole area was filled in with basalt. This cliff here is 900 feet tall. It's a series of basalt flows that occurred and hardened. When glacial Lake Missoula broke, the water came rushing in 600 feet over Spokane and filled up the area of the Columbia River and raised glacial Lake Columbia, and it spilled over in several locations on this plateau. But here, the major part of the water was diverted south because on top of this basalt plateau, we had ice. The Okanagan lobe of the ice sheet was on the top of this plateau right here. It diverted the water along the edge of the ice going south. And it went south far enough to reach the lower Grand Coulee where you have a monocline, which is a dip in the basalt towards the east. And then it connected with that dip, the Coulee monocline, and it started to carve Grand Coulee rapidly from the top of this ridge, 900 feet down and 50 miles and about 6 miles wide at the widest up here in the upper Grand Coulee. Grand Coulee separated into the upper and lower Grand Coulee with a dividing point at Dry Falls. We are standing in upper Grand Coulee, and in the background we have Steamboat Rock. This is a 900-foot high, 1 square mile in area at the top, erosional remnant from the Lake Missoula flood, and shows that large floods leave erosional remnants. We know this from flash floods that go, say, in a field. They'll erode out maybe 90%, but they'll leave some of the field as erosional remnants. We notice similar erosional remnants on the surface of the earth that show that they were formed by a huge flood. For instance, Devil's Tower, 1,000 feet wide and 1,200 feet tall, throat of a volcano in northeast Wyoming. That wouldn't sit there if it was slow erosion over millions of years. It would erode down in probably 10, 20,000 years. But it can be explained by a massive flood, the Genesis flood, eroding the plain sediments all around and leaving that as an erosional remnant. Other erosional remnants on the continents include Ayers Rock in Australia, the Sugarloaf in the harbor of Rio de Janeiro, also Monument Valley. So we see these erosional remnants with vertical walls that show that not only was it left from a giant flood, that's the only explanation, but that it happened not long ago, because vertical faces erode much faster than horizontal surfaces. So you're not going to leave erosional remnants by slow erosion over millions of years. Just like Steamboat Rock is a remnant of one Lake Missoula flood, so are all these other erosional remnants that I mentioned, plus thousands more on the continents that tell us we had a massive giant flood, the Genesis flood, and not that long ago. Well, here we are at Dry Falls between the upper Grand Coulee and the lower Grand Coulee. The lower and the upper Grand Coulee were formed by water, floodwater of the Lake Missoula flood, but in a slightly different way. The upper Grand Coulee went along the edge of the ice sheet for a while, and that's what produced the location of the upper Grand Coulee. And it was probably a combination of the water moving to the south and a receding waterfall that carved the upper Grand Coulee, which is about 20 miles long and 6 miles wide and 900 feet deep. The lower Grand Coulee is a bit different in that we had water coming from the east here, joining the water coming out of the upper Grand Coulee and merging here. And it was flowing down through the lower Grand Coulee, which flowed along what's called the Coulee monocline. A monocline is just a dip in the layers, in this case basalt layers of the Columbia River basalt. And when they dip like that, they crack. It's a weak zone. So the water coming from the east and the north flowed along that crack zone and dug that out, forming the lower Grand Coulee. And in the middle here, you had the waterfall receding right in here, forming Dry Falls, That's about 3.5 miles long, and it receded at least 3 or 4 miles to the point where we see it here. It's dry falls here that especially alerted J. Harlan Bretz that there was something unusual in eastern Washington. He noticed the unusual features for drainages. See, if this is a normal drainage, you wouldn't have a waterfall here. You'd have only maybe little waterfalls and just a general descent from north to south. But here we got a scoured area and suddenly a drop off of 300 feet with 100 deep plunge pools. It looked like a waterfall of a giant flood. And that's what first alerted him. This and another similar area out in the Quincy Valley called the Potholes, which are very similar to this. Along the edge of Quincy Valley, we have a ridge, and the water overtopped that ridge in 3 locations. One formed the Potholes, and it receded about 2 miles from near the Columbia River. Another area is further south called Frenchman Coulee, and he noticed these things which are similar to dry falls and said that is not the result of normal drainages and slow erosion over millions of years. That is caused by a catastrophic large flood. So that's what especially alerted J. Harlan Bretz to postulate this huge flood out here and stick to his guns for over 40 years against practically everyone in the earth science establishment. Now, if you look out this way, you notice that it's been scoured. Again, the Lake Missoula flood provides us some examples or analogs of the Genesis flood. That scouring is kind of like sheet erosion during the retreating stage or recessional stage of the flood early on, when the currents were wide, maybe 1,000 miles wide, moving at high speeds. They would erode big layers of strata, in this case layers of basalt. And then as time goes on, the currents become more channelized as more of the land is exposed above water. And that'd be the same thing here. You had sheet erosion coming from the east, and then you dissected it, like here at Dry Falls, and there's other dissections you can't see out there. So it's similar to the 2 phases of the retreating stage of the flood. Also, another feature of Dry Falls is Umatilla rock. We have a series of potholes from the waterfall going down Dry Falls, but we have a whole nother series over on the other side of this erosional remnant right in the middle here called Umatilla rock. Again, floods leave erosional remnants like at Steamboat Rock. Now here's another idea. This is also against the idea of more than one flood, because that erosional remnant of Umatilla rock down there and Steamboat Rock further up about 20 miles in the upper Grand Coulee probably wouldn't exist if we had multiple Lake Missoula floods. It would have taken it right out. So single floods, as we see in fields, will leave erosional remnants. But if you have more than one, in that same area, it'll eat out all the erosional remnants also. So erosional remnants are evidence not only of one Lake Missoula flood, but the erosional remnants you see on the continents like Devil's Tower are again evidence of one huge monstrous flood called the Genesis flood. Well, here we are just south of Soap Lake, Washington, out from the mouth of the lower Grand Coulee, and we're on the Ephrata Fan, as they call it, which is a huge gravel bar, an expansion gravel bar caused by when the Lake Missoula flood was exiting lower Grand Coulee at 60 miles an hour, over deepening what is now Soap Lake and piling up a big gravel fan that's approximately 15 miles wide and about 20 miles long. And some of these boulders in here are huge. It's a combination of granite and basalt. The northern part of the upper Grand Coulee is granite, and on top of that is basalt. When the water was coming down here, it picked up granite and basalt. Many of these boulders are what is called sub-rounded, which means partially rounded, and that's from the tumbling action, especially the granite boulders. The basalt boulders are more angular because they break off more angular, and when they roll, they just continue to break up. Well, some of these boulders are huge. Like this one behind me is a basalt boulder. Basalt comes in 2 forms, the columns and the more rougher entablature. This is a piece of entablature that was probably ripped off from about 5 miles up Lower Grand Coulee and rolled here. It's probably about 100 feet wide at one time, and it's rolling. It just probably broke off pieces. And that's what you see that is left. That boulder is about 25 feet high and maybe about 40 feet wide. I'm standing on a granite boulder that's sub-rounded. It cracked right in here, but the boulder was probably about 6 feet long and about 4 feet wide and maybe about 3 feet tall. And it doesn't look like granite because it's been well weathered and lichen have been on it, so it's dark. But when you break into it, it's pretty white. Here we are at Frenchman Coulee, about 7 miles northeast of Vantage, Washington. And in this location, the glacial Lake Missoula flood overtopped this ridge right here and dug this canyon as a waterfall that was backing up. It actually overtopped in 3 locations, but it formed a waterfall backing up 2 miles along the ridge in 2 locations, at the potholes further north and here at Frenchman Coulee. Because it overtopped a ridge, J. Harlan Bretz noticed that, well, Quincy Basin had to be full of water for that to happen. And to the south at Drumheller Channels was another outlet. All these are about the same altitude, so Quincy Basin must have been totally flooded in the Lake Missoula flood. And that told him this was a monstrous flood. Quincy Basin is the area of the Afraid of Fan, which covers at least 200 square miles out from Grand Coulee. When the Lake Missoula flood overtopped this area right here, it overtopped it, and when they backed up, it formed an erosional remnant in the middle called the feathers. The feathers are 1 or 2 basalt columns thick of an erosional remnant right in between the 2 amphitheaters that were eroded across the ridge during the Lake Missoula flood. Well, here we are near the Vernita Bridge, about 50 miles northeast of Yakima, Washington. And behind me we see a gravel bar from the Lake Missoula flood. There are probably a few hundred gravel bars associated with the Lake Missoula flood, some of them huge. This one's along the Columbia River, and it was formed when the waters of glacial Lake Missoula spread through the Saddle Mountain water gap up there and formed a gravel bar about 15 miles long and about 5 miles wide, and it narrowed down to where you see the end of it here. And this gravel bar is 100 feet tall. Remember, it's a gravel bar along the Columbia River. It implies that the water was 300, 400 feet deep here, because leaving a gravel bar that thick. And that's what Bretz noticed. He noticed gravel bars like that. He noticed gravel bars on ridges and in odd spots, implying a massive amount of water. And he published a number of papers, just 2 massive papers on just gravel bars. To him, though, evidence was overwhelming that there was a monstrous flood here, even though he never knew where it came from for 10 years. And he stuck to his guns because the evidence is right here. Well, here we are at Palouse Canyon in southeast Washington, overlooking beautiful Palouse Falls, about 200 feet high. This is one of the areas where the glacial Lake Missoula flood overtopped a ridge moving south toward the Snake River. It overtopped the ridge in about 4 locations, but it only dug down in 2 locations. One location is 15 miles to the west of us, where it dug a narrow canyon called Devil's Coulee that's 500 feet deep. Here it dug another canyon called Palouse Canyon, also 500 feet deep. Now Palouse Canyon started wide, about 8 miles wide at the top, and right in here the last 300 feet is very narrow, so it's only 200 feet that was about 8 miles wide and narrow. It's very similar to the profile of the Grand Canyon that starts wide and then is pretty narrow by the time you get down to the very bottom of the canyon. Devil's Coulee and Palouse Canyon represent wind and water gaps cut during the Lake Missoula flood. A water gap is a gorge perpendicular through a mountain or a ridge or even a plateau of which water runs through the gap. A wind gap is like a water gap, but it's not carved deep enough through the ridge for water to flow from one side of the mountain to the other. So only wind passes through it. That's why it's called a wind gap. So several water and wind gaps were formed during the Lake Missoula flood, of which Palouse Canyon and Devil's Coulee are the two best examples here. This shows that a monstrous flood can produce water and wind gaps. In the case of Palouse Canyon, the Palouse River, which used to flow westward down Washtukna Coulee into the Columbia River, after the flood takes a left-hand turn and comes through this water gap formed during the Lake Missoula flood. Now both Devil's Coulee and Palouse Canyon are 500 feet deep, but in the case of Devil's Coulee, it didn't cut deep enough and it left about an 80-foot high rim at the northern edge of it. So no water can go through it. There's a barrier there. So that would be the wind gap. Around the Earth, there are thousands of water and wind gaps cut through mountains and ridges. The Appalachians alone have 1,700 water gaps, and they have a lot of wind gaps cut through those ridges. They're only cut down part way. They're erosional gaps, not faults. And some of these water gaps are spectacular around the Earth. For instance, the Green River cuts through the eastern Uinta Mountains in a half-mile deep, very narrow slot canyon when it could have gone around to the east about 3 miles at a much lower altitude than the tops of the mountains and gone around it. But why did it cut through the edge of the mountains, which are a lot higher? I mean, these are the mysteries of water and wind gaps. And the evolutionary uniformitarian scientists can't explain them, even though they try. They have about 5 hypotheses, all of which have serious problems and can't be proved one way or another. But in this case, with Palouse Canyon and Devil's Coulee, we have a case where a giant flood overtopped a ridge, moving perpendicular to the ridge, coming from the north, and cut a water and wind gap. This is strong evidence that during the Genesis flood, as the waters are going perpendicular to barriers like mountains or ridges or plateaus, and as the waters were draining and channelizing across that ridge, it would easily cut water and wind gaps. So it shows how the Genesis flood can easily form these water and wind gaps, which are all over the Earth, which also shows that the flood was a global flood and not a local event. Well, here we are a few miles from Palouse Canyon, and we're sitting on the ridge that floodwaters of Glacial Lake Missoula overtopped. Out that way to the north is a big scabland tract. As the waters are moving from north to south, they're eroding about 100 feet of silt on top of the basalt, and where they eroded, sometimes they left erosional remnants of the silt. Behind me are 3 silt hills that are streamlined by water. They're orientated at about 3 times as long as they are wide. They're lens-shaped, and they're pointed towards the north, and they kind of flare out towards the south, almost like prows in ships pointed upwind into the face of the wind. These are great examples of the hundreds of streamlined silt hills within the flood path of the Lake Missoula flood. Well, here we are in the Snake River Valley, near where the Palouse River enters the Snake River just behind me, and we're standing on a gravel bar. There are numerous gravel bars in the Snake River Valley caused by the Lake Missoula flood. The flood backwashed the river up to around the Lewiston-Clarkston area, and then it came back. We're standing on one of those bars, and this bar has ripple marks on it. There are about 100 of these on gravel bars in the flood path. They're difficult to see on the ground, but from the air you see them quite clearly. That's probably why J. Harlan Bretz, I read all his scientific journal articles and his monograph on the Grand Canyon, and I don't think he mentions anything about ripple marks on top of these gravel bars. He had to do most of this research on foot, and it's probably why he lived to be 98. But he outlived all his critics. He published from about 1923 to about 1932. He was opposed by practically everyone, and those who believed him kept quiet because of the fear of the establishment that strongly believed in uniformitarianism. It's actually not too different today for people who believe in the flood. When they accepted the Lake Missoula flood in the 1960s, he was a hero from then on, but he had to endure a huge amount of criticism and rebuke and rejection by the geological establishment. With the advent of aerial photographs in the 1960s, they were able to see the ripple marks plainly on top of the gravel bars, again giving evidence that this whole valley here was filled with water at one time, moving at high speeds, forming these giant gravel bars on a scale so much larger than modern rivers. So this was another big piece of evidence that helped convince the world, the geological establishment, that the Lake Missoula flood was real after rejecting it for 40 years. Well, here we are in the lower Tucannon River Valley, just up from the Snake River. And here we are seeing some rhythmites from the Lake Missoula flood. These are rhythmites of 3 units of gravel of various sizes, followed by sand and then silt, and then gravel, sand, and silt again, and several times up there. And some places it's chaotic, in which the gravel layer thickens and thins. So this represents when a large lake was forming around Pasco because the water couldn't get out of Wallula Gap, formed a lake 1,000 feet deep, and it was backwashing up all these tributary valleys, including the Tucannon River Valley. And when it backwashed up, the currents were going pretty fast, and they carried a lot of gravel, mainly basalt gravel, upward. And you could see the force of the current going up this valley by that rock right up there of basalt. But as the level of the lake over Pasco decreased, the water come back down, and it eroded out most of these rhythmites, because this sequence you see here had to continue clear across the valley over there and fill up this whole valley. As the waters are coming back down the valleys as the lake was draining, it eroded about 98% of the rhythmites that were formed early in the flood by pulses. Each rhythmite's probably one pulse, where the water was moving faster, depositing the gravel, sand, silt, and then it slowed down, and then another pulse come and deposit gravel, sand, and silt. When it got further up the valley though, the gravel usually disappeared and the rhythmites became mainly sand and silt rhythmites. And this is typical of all the valleys, like the Yakima River Valley and the Walla Walla River Valley. At the entrance to these valleys, you find gravel in the rhythmites. You get further up, you lose the gravel because the currents were slowing as they got further up the valley. So as the lake level was receding and the water was coming out of these valleys and was picking up speed, it eroded 98% of the material, just leaving this bank here and in a few other spots. Well, here we are in the middle of the Walla Walla Valley, about 2 miles south of Loudon, right near the head of Burlingame Canyon, and we're sitting on a ridge of rhythmites formed during the Lake Missoula flood. These rhythmites were believed by J. Harlan Bretz and Victor Baker to each be a pulse of water that came up this valley here when a large lake developed just to the west of us around Pasco, because the waters of glacial Lake Missoula couldn't get through Wallula Gap. So it formed a lake 1,000 feet deep approximately, and it backwashed up the Walla Walla Valley, the Yakima Valley, the Snake River Valley, the Tucannon River Valley, and other valleys, forming a series of these rhythmites. A rhythmite is defined as 2 or more couplets of the same sediment. In this case, it's sand and silt, over and over again, sand, silt, sand, silt. And in Burlingame Canyon, there's approximately 40 of these rhythmites. Burlingame Canyon was formed by accident. In the 1920s, this irrigation ditch here on this ridge of rhythmites filled up with tumbleweeds during a strong wind, and they were afraid that it was going to cause a flood by blocking up the water and eroding these fields. So what they did is they bled the water off in an irrigation ditch just beyond that house that is about 100 to 150 feet long. So they bled it off, and within 6 days it cut a canyon in this soft material 125 feet deep and about 500 feet long. It was in Burlingame Canyon that Richard Waite found that layer of ash about the top of the 11th rhythmite from the top. He thought that you couldn't have an ash layer from Mount St. Helens occurring at the same time as one Lake Missoula flood. He felt that each rhythmite must have been a separate Lake Missoula flood. Now, the previous interpretation by J. Harlan Bretz and Victor Baker was that each rhythmite was one pulse coming from the large lake that suddenly ponded around Pasco. Now, that lake lasted about 5 days. The pulses would come from the water level going up and down like this, because the channel of the Lake Missoula flood through eastern Washington would converge and diverge. And every time it converged, the water would go up in the lake, and when it diverged, it went down. When it went up, it'd send a pulse of water up, and that pulse would form a sand silt rhythmite, and then it'd slow down, and then another pulse would be on top of that, forming the 40 series of rhythmites. That's what was originally believed, but Richard Waite turned that all on its head and said that each rhythmite has to be a separate Lake Missoula flood. One Lake Missoula flood sounds too catastrophic, but if you have multiple Lake Missoula floods, it sounds more normal or business as usual, kind of uniformitarian in a sense. They like cycles, they like multiple ice ages, and I think there was a desire to have multiple floods. From Burlingame Canyon, they deduced 40 Lake Missoula floods. In another valley, north of Lake Roosevelt, the Sandpoil Valley, they found 90 or more rhythmites of a different nature. So the number of floods went from 40 to 90 and rounded off to 100, just at the peak of the last ice age. This represents probably at least 5,000 years of time, Earth history, just at the peak of the ice age. That's why it's important to examine this issue, because it contradicts biblical Earth history, the short time scale from the Bible. So that brings up the question, how many floods were there? Were there 1 or 40 or 90 or 100? Just at the peak of the last ice age, not to speak of all the other ice ages they talk about. So that's why it's important to look at these rhythmites and how they lay. One thing you notice in this valley is that we're on an erosional remnant. It's so flat that they have an irrigation ditch at the top, and this irrigation ditch starts up by Walla Walla about 15 miles to the east and goes along this ridge. It's so flat. But you look out to the north and the south, and the rhythmites have mostly been eroded out. So 90% of the rhythmites are gone. But did the rhythmites get out when Lake Lewis went down and the water come out? I believe that is the case. But if each rhythmite represents one flood, then the first flood lays up a rhythmite over this whole valley and then gets eroded out. Then a second one comes up, gets eroded out, probably along to the south and north, and so on 40 times. Just happens to lay 40 rhythmites right here, but they get eroded out to the left and right. If that was the case, this ridge here would not have horizontal rhythmites like this. They would be stacked and draped on each other, and then you'd have erosion through it as the waters drain back out to the west. You should see a lot of cut and fill, but because of Burlingame Canyon cut perpendicular to this ridge, these rhythmites are very even and smooth and horizontal, which is strong evidence that you didn't have multiple floods, but just one main flood that carpeted this whole valley with these rhythmites, each one a pulse, as the water was filling up in Lake Lewis around Pasco and sending pulses up, and then mostly eroded 90% of it out as it was moving back to the west. And some of the evidence that occurred is that Down near Loudon down there and other places, we have streamlined silt hills from the whole area being filled with water and streamlining some of the rhythmites. It was eroding most of them out, but pieces they didn't erode were streamlined, going from east to west, west being down current. Here we are on the backside of Burlingame Canyon, and you can see the rhythmites from this position. They're very evenly bedded and horizontal. They're not draped on each other for multiple floods in this one spot. Again, indicating one large flood deposited these rhythmites horizontally over this whole area. The geomorphology of these rhythmites is not the only evidence for one flood. Besides the geomorphology of the lake bottom sediments in glacial Lake Missoula, north of Missoula, also the rhythmites thin with altitude. They go from 6 feet thick at the bottom to about 6 inches thick at the top, which is what you expect as the lake was waning. It was built up fast and then it was slow. So you expect the pulses to slow down with time. Well, here we are on a cliff above the Yakima River between Sunnyside and Granger, Washington, just south of Snipes Mountain. We're standing on a cliff of about 40 rhythmites of the Lake Missoula flood. And these rhythmites are generally thicker on the bottom and thinner at the top. These were formed by the Lake Missoula flood pulsing up this valley from the faster and slower flows. But then in 1980s, they discovered, well, they knew about it, but they noticed a white ash layer that you can see near the tops of these rhythmites. And this ash layer is from Mount St. Helens. One scientist said, well, the one Lake Missoula flood, which was believed by J. Harlan Bretz and many others for many years, and that is one Lake Missoula flood would be a very rare event. Mount St. Helens is another rare event. So what's the odds of 2 rare events occurring at the same time? So they said that ash must represent instead a time when between floods, when the ash just laid on the surface over this whole area. So each of these rhythmites was then considered separate floods. And if you have 40 rhythmites in the Walla Walla and the Yakima Valley, you have 40 separate glacial Lake Missoula floods. And then the ash was supposedly called the Rosetta Stone for the interpretation of how many floods there were, from 1 to 40. The ash, which was the Rosetta Stone, or their main evidences, if it sat out on a rhythmite from one Lake Missoula flood and Mount St. Helens went off, and that ash was all over the same area, about 4 inches thick, and you had to wait 40 to 80 years for glacial Lake Missoula to fill up, being blocked by that Cordilleran ice sheet in the Purcell Valley of northern Idaho. If you waited that long, this ash would turn to clay, or it would be mixed with other wind-blown material, because the wind blows a lot in this area, or it disintegrated, blow away. In fact, we have an experiment to show that this ash couldn't have been sitting here for 40 to 80 years, and that these rhythmites are not from separate Lake Missoula floods, because Mount St. Helens went off in 1980 and spread ash over this whole area, up to, I think, about 8–10 inches thick up near Richfield to the northeast. And since then, this ash has turned to clay, it's blown away, it's been mixed with some of the surface sediments, and so you can hardly detect it anymore. So this ash can't lay around for 40 to 80 years for glacial Lake Missoula to form again. Then there's a question if this was a deposit of one glacial Lake Missoula flood. How do you account for the rare event of the ash layer being about the 11th rhythmite from the top being in these layers? How do you get that? That's a rare event, the Lake Missoula flood's a rare event. Well, here's how I think it happened in one flood. That lake centered around Pasco, Washington, 800 to 1,000 feet deep, was an instant lake. It lasted about 5 days. I found out that when they fill up reservoirs behind dams by water, it causes earthquakes. In fact, there's one earthquake in India by the slow filling of a dam that caused a 6.2 magnitude earthquake that killed about 80 people. So it's well known that filling of reservoirs cause earthquakes. You'd expect that this big lake formed centered over Pasco and backwashing up this valley and the Walla Walla River Valley would be so heavy, and it was so fast that you'd cause some massive earthquakes. But secondly, I found out that when a strong earthquake goes off, it can set off a volcanic eruption for volcanoes that are ready to go off. and Mount St. Helens erupts every 100 to 150 years. So here's a scenario. That instant lake 1,000 feet deep formed all these earthquakes, and those earthquakes set off Mount St. Helens, and that went off and sent ash over this whole area. And that's why you find it near the top of the rhythmites, near the end of this lake that sent these pulses up here. So that accounts for the ash being about the 11th rhythmite from the top occurring at the same time as the Lake Missoula flood. The ash as evidence of multiple floods is poor evidence. And there's lots of other evidence in this area that there's only one gigantic Lake Missoula floods and possibly a few smaller ones afterwards, but just one giant Lake Missoula flood. Well, here we are in front of Wallula Gap, which is that way, where the Walla Walla River runs into the Columbia River. And we are in a railroad cut here, cut through a small patch of rhythmites. According to the literature, there's about 20 rhythmites here, sand-silt alternations. But these rhythmites aren't all that distinctive. You can't see them very well because you've had a lot of sloughing and probably a lot of movement here. Not like in Burlingame Canyon, the Walla Walla Valley, where they're very even and flat. That's what the rhythmites really look like underneath everything. So it's interesting about this patch of rhythmites right here in that if each rhythmite was one flood and the water come rushing down to the north at high speed trying to get through Wallula Gap, why would you have 20 of them stacked up in one small location here if each rhythmite represents one glacial Lake Missoula flood? It really makes no sense for that because it should have eroded each, maybe the first rhythmite that got ponded left here. The second flood would come and erode that all out. So it doesn't make sense for a stack of 20 of them to be here. So this is another evidence among many for just one glacial Lake Missoula flood. Another piece of evidence for one flood is called clastic dikes. You see an example of it right here where you got a layer of material that is going perpendicular to the rhythmites. You see this at this section and practically all sections in the Yakima Valley, River Valley, and the Walla Walla River Valley. In the Burlingame Canyon, it can be 6 feet in diameter, and they're generally sand silt. They're almost like the rhythmites that are kind of layered, but vertically. You'd expect this in one flood because if they're all laid down at once, this water would be pretty saturated with water. And so as the lake level went down, you'd expect the pressure above it to decrease and water to come oozing out of it and forming these what's called clastic dikes perpendicular to the rhythmites. And that's what you see. They go from in Burlingame Canyon, they go from the bottom to the top. Just like these cross number of rhythmites. Now, if each one of these rhythmites was laid down by one flood, you would have these clastic dikes go up to the top of one rhythmite, maybe that thick, stop. Then you'd have another layer put on it and another set of clastic dikes go up and stop at the top. So they should all stop at the top of each rhythmite if each rhythmite was from one flood, and they don't do that. They go all the way from the bottom to the top, indicating one flood and not separate floods over thousands of years. Here we are southwest of Wallula Gap through the Horse Heaven Hills where the Columbia River flows through. Now, it was this gap, which was narrower at one time, of which the waters of the Lake Missoula flood coming down from the north couldn't get through here fast enough through this gap. And so it backed up a lake in the Pasco Basin area up to 1,000 feet deep that lasted 5 days. They call it Lake Lewis. And when this lake ponded, it sent water washing up the tributary valleys like the Snake River, the Tucannon River, the Yakima River Valley, and the Walla Walla River Valleys. And that's how those rhythmites were formed, as this water was ponding. So it ponded in about 3 days and then it emptied in about 2 days. Now, not all secular geologists believe in multiple floods. In fact, a team from the University of Alberta in Edmonton under John Shaw, 6 geologists in all, came down here in the late 1900s to investigate it afresh because it was still controversial whether there was one or many. And they examined the area and concluded that there was only one major Lake Missoula flood. And they published it in the journal Geology, I believe in 1999. And so to them, there was plenty of evidence that overwhelmingly said one flood. But of course, it was a very controversial article, and they got a lot of letters to the editor and a lot of flack for it because of the controversy of it. But they concluded, and I would say they came in this area fresh without any biases and came away with the evidence that there was just one large Lake Missoula flood. Before the Lake Missoula flood, the Columbia River came through this gap, but the gap was narrower. But during the Lake Missoula flood, it eroded it wider and eroded some of the top off and created a few erosional remnants. And after the flood, the Columbia River continued to go through this gap. The waters of Lake Missoula flood were 1,000 feet deep coming through this gap. And then they spread out in the Umatilla-Hermiston area, and then they ponded again, going through the Columbia Gorge, forming another lake in the Umatilla-Hermiston area. And the water was rushing through the Columbia Gorge about 80 miles an hour, and there was 1,000 feet deep also. It widened the gorge, which probably was more of a V-shaped gorge, and it made it more U-shaped, and that's why we have all these nice waterfalls coming in on the sides like Multnomah Falls. And as the water exited the Columbia Gorge, it spread out in the Portland-Vancouver area and dropped a huge load of gravel, forming what's called the Portland Delta. 200 square miles of gravel, some of it's really huge stuff, and about 300 feet deep or more in that area, which part of Portland and Vancouver are built on. And then, as the Lake Missoula flood was waning, the narrowing of the flood cut the Columbia River channel down through that Portland Delta to where the Columbia River flows right now. As the flood moved through the Portland-Vancouver area, it was about 400 feet deep, and it backwashed up the Willamette Valley clear past Eugene. In the flood, we had all these icebergs filled with rocks. The icebergs grounded all the way through eastern Washington to the Columbia Gorge, and in the Willamette Valley we had thousands of erratics, a lot of them granites from the Grand Coulee area or northern Idaho, or argillite boulders from Montana and Idaho that grounded in the flood path. Then after it exited the Willamette Valley, it spread to the Pacific Ocean down what is now the Columbia River and exited on the continental shelf, creating a small canyon on the continental shelf. Well, here we are in the beautiful Willamette Valley, up along the foothills of the coastal mountains. And before us we have an erratic boulder that was deposited during the Ice Age, but we're 150 miles south of the boundary of the Ice Age, which was at Olympia, Washington. So how did this erratic boulder get down here? An erratic boulder is a boulder that does not outcrop in the local area. In fact, this type of rock is called argillite, a slightly metamorphic shale. You can see the platy shale look of it, but it's been heated up and hardened some. This type of rock doesn't even outcrop in Oregon. It got here by the Lake Missoula flood, and it brought all these erratic boulders, and the Willamette Valley has hundreds of erratic boulders, of which this one is the largest one. Right now it weighs 90 tons, but it used to weigh 160 tons before tourists chipped parts of it off. That's how this erratic boulder got here during the Lake Missoula flood, which indicates that there was an ice age that formed the lake and caused the Lake Missoula flood and deposited this erratic here. It shows that there was an ice age that was caused by the Genesis flood, and it's just one of the pieces of evidence for this ice age, which still is unexplained by uniformitarian scientists, but yet we have a model that it can explain it as the climatic aftermath of the Genesis flood. And so it's just one more piece of evidence for this ice age caused by the rapid post-flood ice age. Well, we learned several things by studying the Lake Missoula flood. We find out by studying the Lake Missoula flood just how devastating the Genesis flood was, but we have to extrapolate out. Secondly, we can study what this flood did. We can look and see some of the landforms or features it formed, and we can relate these to some features on the surface of the earth formed during the Genesis flood so that we can understand that floods formed these features. Another aspect of learning about the Lake Missoula flood is that we find out why mainstream scientists will never accept the Genesis flood, because the evidence for the Lake Missoula flood is obvious all over, and yet they rejected it for 40 years. It's quite a history showing why they will never see evidence of the Genesis flood. This worldview retarded the science of geology with the Lake Missoula flood, and I believe with other issues in geology. But they don't realize that it's a worldview that they're expounding, and it's based on assumptions that are unprovable. And the Lake Missoula flood was a strong assault on uniformitarianism. They can't see catastrophism because of those uniformitarian glasses on it. With those glasses, during Bretz's time, and even now, we don't expect them to find evidence for the Genesis flood. In fact, some of them say there isn't any, because of that strong bias that just clouds their mind. And so that's the way it is in geology during the time of Bretz, and the way it is now.